Bismillahirrahmanirrahim. Assalamu alaikum students. Our today's lecture is about combinational logics, logical circuits. Logical circuits can be maybe combinational or sequential. In this today's lecture, we will discuss about combinational logic circuits. Combinational logic circuits mostly consist of inputs. Combinational circuits there should be logic gates and outputs output variables. Combinational logic gates react to the values of signals that are provided at their inputs and produce the value of output signal, transforming binary information from the given input data to a required output data. As we can see from this block diagram, 4.1 block diagram of combination circuits, there is n number of inputs combination and m number of outputs of the combinational logic circuits. And this combinational logic circuits, the input binary variable comes from the external source, and the output at output point, the m output variables are produced by the internal combinational logic circuits and go to an external destination where the data is required. Each input and output variable exists physically as an analog signal whose values are interpreted to be a binary signal that represents a logic 1 or logic 0. And we can say that the simulators, in case of simulators, only zeros and ones are the required, not the actual analog signals are used for actual simulators. In a lot of applications, we can say that source and destinations maybe are of storage components like registers. If the registers are included with combinational logic circuits, then these combination circuits becomes a sequential circuits, which we will be considered in the next chapter. Combinational logic circuits, if there are n number of inputs or input variables, then there should be 2 raised power n possible combinations for the input values of the or input value of that combination circuit. If n inputs, as we know that the possible combinations are equal to 2 raised power n. N, if n is 2 inputs, then 2 raised by 2, there will be 4 input combinations possible that can be used for the to run that combination circuit and produce the m4 or m output variables. And thus a combination circuit specified with a truth table, and we can also construct truth table by using these combination circuits, and we can explain these things about the logic gates and output variables and input variables, and how we can construct the truth table and the function of the system, and by using that function we can create different truth tables and logic diagrams, and we will see in the next slide. And there is analysis procedure, that how we will analyze a given logic diagram for analysis purpose, that how to obtain the output Boolean function from a logic diagram, and how we can find out the logic function of the from that diagram, and how to convert that diagram and function to generate a truth table for that system. The analysis of combination circuits requires that the function on which that circuits is implements this task starts with a logic diagram and different set of Boolean functions, truth tables, possibly different explanation of operations are required to know that how this function is going. And to analyze the process, some points we should have to know. The first step in the analysis is to make sure that the given circuit is combinational or not. First of all, we have to determine that the given circuit is a combinational and not the sequential circuit. The basic block diagram of combinational circuit has logic gates with no feedbacks. Paths are memory elements. It means the logic circuits only consists of input variables, output variables, and logic gates. There are no feedback paths or memory elements included in the combinational logic circuits. And a feedback path, we can say that a feedback path is a connection from the output of one gate to the input of another gate that forms part of the input to the first gate. Feedback path in a digital circuit define a sequential circuit. These feedback paths are existed in sequential circuits, and if the diagram is verified, once we have verified that the diagram is that for a combination circuit, then we can proceed to obtain the output Boolean function or truth table of that function or of the given logic diagram. In the function of the circuit, it is which is the circuit which is given circuit which is under investigation and we have to analyze that circuit. Then it is necessary to interpret the operation of the circuit from the derived Boolean functions or truth tables. The success of uh, the investigation and to determine that how this circuit is working, it they are included different steps which we have to follow to obtain the output Boolean function from a logic diagram. We will proceed, and these steps here are according to that label all the output in gates that are the number of gates which are included in the logic diagram. We have to label those the outputs of those gates that are a function of input variable with binary symbols but with meaningful names. And then we have to determine the Boolean function for each output gate. That we will determine the function of each output gate and then label the gates that are a function of input variables and previously labeled gates with other arbitrary symbols. Find Boolean functions for these gates. And we have to use those previous functions to form the Boolean function of the next gate's outputs. Repeat the process outlined in step 2 until the outputs of the circuit are obtained. By repeating the substitution of previously defined functions which obtain the output Boolean function in terms of input variables. That by using previous function of the gates, we can obtain the final output function of the given diagram from in terms of the input variables. Okay, now we see the let's see an example of the combinational circuit. In this example, we have to analyze the combinational circuit which is given in this diagram. In this analysis, we have to find out the output function f1, f2 by in terms of input variables a, b, and c. The outputs of various gates are labeled with intermediate symbols like we can see that T2, T1, uh, F2 prime, T3. And by using these easily, and we can easily drive these functions in terms of input variables. And we can say that if we use the annotations, T2 will be equal to as it's the output of an AND gate, it will be equal to the product of A, B, and C variables. And T1 is the output of an OR gate, so it will be the sum of A, B, and C. A plus B plus C. And similarly, we can find out that what will be the outputs of the given function, as the f2 will be equal to, as these are the AND gates, AB plus AC plus BC. These three gates are outputs are becoming the input of an OR gate. So f2 will be equal to the sum of the product of the given AND functions. So which will be equal to this thing, AB plus AC plus BC, and the values of T1 and T2 are also as, and the T3 will be equal to the complement of F2 into T1, complement of F2 into T1, and then the function F1 will be equal to T2 plus T3, T2 plus T3, and then we will put the values of given functions in terms of input variables, and which will become this is, and in the form of, in terms of input variables, our output function will be obtained. F1 and F2 is already in terms of input variables. And so by using this process, we can find out the function, Boolean functions, and implement a circuit to recognize the familiar functions. And then finding a Boolean representation of a circuit doesn't, we can say, provide insight into its behavior. We have to find out the truth table of that given function, and to find out the truth table, we have to follow different functions, that how to construct a truth table of the given Boolean function by using the derived output functions and the logic diagram of the given example. Driving the truth table from the logic diagram, we can easily drive this table of the given last example, which we have just uh, find out the Boolean function, output function in terms of input variables. And to find out the truth table, we will proceed by determining the number of input variables in the circuit. First of all, to construct our truth table, we have to find out the total number of input variables. We know that the input consists of three variables A, B, C. So the combinations of three inputs will be equal to 2 raised to power 3, which is equal to 8 input combinations will be as listed in this table of 4.1. Now we have to find out the value of output functions, which will we have to, in terms of input variable, we have already created the given function. Label the outputs of the selected gates with arbitrary symbols, as we have labeled the outputs of the gates T1, T2, T3, F2 prime, F2, and F1. Obtain the truth table for the outputs of those gates which are a function of the input variables only, which are the functions. First of all, we have to obtain the function outputs of the function into which are the directly combination or functions of the input variables like T1, T2, T3, F2, and F2 prime. So by using these functions, we will find out the output values of these functions easily by using the function which we have recently derived in the last slide, as by using these functions of F2, T1, T2, T3. Okay, after finding out these functions, proceed to obtain the truth table for the outputs of those gates which are a function of previously defined values until the columns for all the outputs are determined. All the outputs, these main outputs are F1 and F2. Until we have determined these outputs, we have to proceed to find out the values of output values of the given gates in terms of our truth table, and then we will easily define that how this given logical basic logic circuit is working and how its output is responding according to the input variables. Next, we have to consider that the design procedure, that how to design of a combination circuit starts, and how we have to start, and from which point we will start, and how we will construct the given circuit from the given information which is given. The design of combination circuit starts from the specification of the design objective and culminates in a logic circuit diagram or a set of Boolean functions from which the logic diagram can be obtained. The main procedure which we will follow consists of the following some steps we will use to find out from the specifications of the circuit, determine the required number of inputs and outputs, and assign a symbol to each. That first of all we have to during the design process we will use the given information and find out the specification and determine the required number of input variable and outputs and assign a symbol to each input and output. Then drive the truth table that defines the required relationship between inputs and outputs. Then we will drive a truth table which will de- define the required relationship between the inputs and outputs. After that truth table, obtain the simplified Boolean functions for each output as a function of the input variable. And then draw the logic diagram and verify the correctness of the design manually or by simulation. By we can apply the given inputs and find out that after applying the given input value, are we getting the output values of the function which are mentioned in the truth table which we have derived from the given information of the circuit. A truth table for a combination circuit consists of input column and output columns. The input columns are obtained from the general formula of 2 raised to power n binary numbers for the n input variables. The binary values for the outputs are determined from the stated specification. The output functions mostly specified in the truth table give the exact definition of the combination circuit. It is important that the verbal specifications be interpreted correctly in the truth table, as they are often we have to use, and that which functions are used in the given output functions. The output binary functions which are listed. Okay, after the construction of the truth table from the given function, we simplify the functions which are given. For example, the output binary functions listed in the truth table are simplified by any available method, like such as algebraic manipulation or K-map method or computer-based simplification programs. We can use these methods to simplify the output function. There is a variety of simplified expressions from which we can choose the expression which are using minimum number of gates and input variables. And different applications which contain the criteria will be served as a guided process in choosing and implementation of different given methods to simplify the system. And in this example, we will first use as a code conversion example, which is we will be used as a design example in which this code conversion. First, we can list the relation of the BCD and XS3 code in the truth table. As this is the conversion from BCD to XS3 code, and first we have listed the truth table for this conversion. In this truth table, we know that BCD for BCD, the input are A, B, C, and D, and outputs are designated as W, X, Y, and Z. As the given combinations which are assigned to BCD codes and XS3 codes are listed in the table, BCD codes are assigned with A, B, C, D, and XS3 codes are assigned with W, X, Y, and Z. and each code uses 4 bits to represent a decimal digit. There must be 4 input variables and 4 output variables. So we have designated the input variables as A, B, C, D, and outputs as W, X, Y, and Z. The truth table relating the input and output variables in terms of given input variable. The bit combination for the inputs and their corresponding outputs are obtained easily by using that how this output will be equal to which combination by using the K-map method. In the K-map method, we will mark the each one of the 4 maps that the one marks inside the space are obtained from the min terms that make the output equal to 1. And we will in the given truth table as described at this point. Here we can see that this one is marked where the min term is equal to 1, and we can see that this combination is as uh, 0, 0, 0, and 0. The output is equal to 1. So this one is marked as here. The ones are obtained from the truth table by going over the output columns one at a time. For example, the column under output Z has 5 ones. Therefore, the map for Z has 5 ones. 1, 2, 3, 4, and 5 ones. Uh, each being in a square corresponding to the min term that makes Z equal to 1. And the 6 don't care min terms 10 through 15 are marked with an X. These don't care conditions are as we have considered only 0 to 9 uh, BCD combination. So the remaining 6 combinations are treated as do not care conditions, which are marked with the X symbol here. And so we can simplify the function into sum of products from a list form is listed under the map of each variable. This is easily mapped. And after mentioning the do not care condition, we can map these squares easily, and we can see that the group of these 8 will be constructed, and the output which will give the output function of we d prime, and z will be equal to d prime. And when we will move to the next output y, in the y we see that 1, 1, 2, 3, 4, and 5 ones are listed in the map, and 6 do not care conditions are also listed, and by using this we know that the y will be equal to cd plus c prime d prime. And we know we have studied previously that how we have to combine these squares and how to find out the output equations of the functions. And after this, the remaining 2 outputs of x, w, and x are also combined and obtained by using this given formulas, and obtaining the output functions are obtained, which are we can say that the uh, easiest or simplest, and we can also again more simplify these functions by using these equations as z is already a simplified function. Z is equal to d prime, y is equal to cd plus c prime d prime, and from this cd plus we can convert this into a product into an or operation, and then x is equal to b prime c plus b prime d plus b c prime d prime, and we can convert that thing into easily these functions. And then by using these function diagrams, we will construct a logic diagram that implements in this circuit. The logic diagram that implements these expressions, we can easily see this diagram which is based on and or and not gates, and not counting input inverters. The implementation in sum of product form requires 7 AND gates and 3 OR gates, and this implementation we can implement different we can implement this these functions in different ways, and we have to remember that the outputs should always be remain in the same form, that outputs cannot be changed, and we have to find out the same outputs for these things, and this is the logic diagram for BCD to access3 code converter. As after designing this example, inshallah, in our next lecture, we will see about the binary adder and subtractors. As most of the we know that digital computers perform variety of information processing tasks, and inshallah, in our next lecture, we will see about binary adder subtractor circuits, and I will discuss that how they work and how we can obtain their output functions and those tables. Okay, students, take care. Allah Hafiz. Assalamu alaikum.